Okay, hello everyone. Welcome back to Chemistry 3120. Today's lecture 8, and we're going to be talking about oxidation. So we're changing things up completely. We've been talking about reduction for many lectures. So welcome to lecture 8. Oxidations. Okay, so we're going to be talking primarily about the oxidation of alcohols. It's one of the most common types of reactions that is used in organic chemistry. So oftentimes we want to take an alcohol and we want to oxidize this to either an aldehyde or a carboxylic acid. And there's many different ways in order to do this. So we'll talk about some of those main methods today. Okay, so oxidation of the hydroxyl group. All right, so let's take a look at a classic oxidation mechanism that is known as Jones oxidation. Jones oxidation involves taking an alcohol and reacting this with chromium trioxide under strongly acidic conditions. Often we use things like H2SO4, sulfuric acid, and water. It's pretty harsh conditions. The chromium trioxide is also pretty harsh. It's a very strong oxidizer, but it's a very powerful reaction. So this reaction will essentially convert your carboxylic acid, if it's a primary hydroxyl, all the way to a carboxylic acid. Now let's think about how this reaction will happen. Maybe I'll start down here. And the chromium trioxide is in a +6 oxidation state. So it has a lot of affinity for electrons. So if we take our alcohol, the first thing that's going to happen is that you're going to get your nucleophile and it's going to react with chromium in its +6 oxidation state. Okay, so nothing too crazy there. Once that reacts, we are now going to have your oxygen chromium bond like I'm showing, and you have this oxygen that's positively charged, so we need some type of base to remove that. In solution up there, the best base that we have is water. So water is going to be around and can pick up that proton to generate this species here. And what I'll do is I'm going to draw this chromium in just a slightly different way. Actually, no, I'll just draw it the same way. And we need to now go to an aldehyde. So how are we going to generate an aldehyde? So in order to generate an aldehyde, we need to remove some of these protons, right? So we're oxidizing. So what we're going to do is we're going to imagine the double bond that's nearby. It's going to come and pick up this proton here in an intramolecular fashion, form a double bond, and then you can break that oxygen chromium bond. So if you do that, you're now left with an aldehyde plus your chromium byproduct. Now, I mentioned to you that we need to go all the way to the carboxylic acid. So we've gone part way in which we've gone to the aldehyde, but how do we get another oxidation round happening? And if you think back to the first step involved taking this alcohol, reacting it with chromium. So we had a good nucleophile here. But if you look at your aldehyde, it's not really such a good nucleophile. And furthermore, you know that this is actually a fairly good electrophile. So how are we going to do this? So keep in mind that aldehydes, in the presence of water or alcohol, especially with acid, have an equilibrium associated with it. They can form water can come and attack, and you can form things like acetals. In fact, one of the very first reactions we looked at in this class was protection of an aldehyde using an alcohol under these various types of conditions. The only difference here is that water is acting as an alcohol. It's the smallest alcohol out there. So there's an equilibrium always between generating the acetal from the aldehyde when you have water in solution. Okay, so that means that we can take that aldehyde and we could draw a mechanism for that. You would know how to do that. And you're going to have this acetal in solution. And once this is in solution, you can now imagine how this will react with the chromium trioxide. And you can see here that it's going to follow a very similar pattern to what I've drawn on top, directly above it here. So now one of these OH groups will come and attack the chromium. Positive oxygen here, just like we'd seen before. So water is your best base. And how are we going to go from this species to the final carboxylic acid? Well, that's going to follow a similar elimination type of mechanism. So you're going to basically take, if you had a double bond here, that would work fine. Here we have an O-, that's fine too. So this will come pick up this hydrogen here, which is a proton, and it's going to do an elimination like I'm showing you here. Okay, intramolecular elimination, proton, form a double bond, break that oxygen chromium bond. You do that, you're going to generate your carboxylic acid. All right, good job, congratulations. So when you recycle back that chromium, so you've done the full oxidation. So this is one example where if you take a primary hydroxyl group, primary hydroxyl groups can be partially oxidized to aldehydes. They are fully oxidized to carboxylic acids. Okay, that makes sense. Gone through that mechanism. What about secondary alcohols? What if we had an R group here and then we had a secondary alcohol? What would that look like? What do you think? Have you thought about it in your head? Okay, so if you go through this mechanism, and if you had an R group here, imagine an R group here, R group here, okay, you do this reaction, then you're going to have an R group here. So that's going to mean that you have a ketone. All right, so they can be oxidized to a ketone. Can we further oxidize those ketones, however, like the second step? Well, if we have a ketone, we're going to have no problems making a ketal, okay? Imagine you're going to have an R group here instead, and you can go through these initial first steps. However, you're going to be stuck at this stage here because you cannot deprotonate. There's no proton there. You're going to have an R group. So everything is going to be reversible and go back. And so therefore, secondary alcohols can be oxidized only to a ketone. And last thing I just want to mention is tertiary alcohols cannot be oxidized. And if you don't believe me, try the mechanism where you have R group here, another R group, and try doing that. You won't be able to do that elimination reaction. All right, so that is how this group works. Very strong oxidizing solution. Another one that's related to this one is potassium permanganate, KMNO4. So other strong aqueous potassium permanganate and something similar to chromium trioxide. Is this compound here, which is like a dichromate. And it would behave very similarly to what I've shown you there in terms of a mechanism. Now, a couple things I want to point out about chromium. Chromium in this oxidation 6 is actually very toxic. It's a potent mutagen. It actually is so strong that it will actually oxidize your DNA, particularly guanine. And then what happens is that this can result in mutations and can alter, the genetic code. So it's a potent mutagen. And furthermore, if you're doing this, you have to use strong acid. So that's also, you have to be careful with that, of course. But if you have a molecule with many functional groups on them, you might have acid-sensitive groups, or you might have protecting groups that would come off of acid. So it's a very harsh condition, and it's used when you really want to oxidize something in brute force. It's certainly maybe not the most elegant and safe method to do so. The other thing about the Jones oxidation, I should write that this is called Jones oxidation. Is because it's done in acidic conditions with water, if you have a primary alcohol, you're going to go all the way to the carboxylic acid right here. However, you might have instances, or you will likely have instances, where you want to stop at the aldehyde. And you can't control that if you're doing this in strong aqueous conditions. So are there other ways to do this reaction so you stop at the aldehyde? Right? What do we need to exclude from the system if we want to oxidize it only partially to the aldehyde? How can we avoid oxidation from the aldehyde to the carboxylic acid. Well, the obvious thing to do would be to look at what's needed. You need water for that to happen. So use anhydrous conditions. Okay, so do something where you don't have water in solution. So a couple good examples are some molecules that retain that chromium character where it's very reactive, but you can do them under anhydrous conditions. So one of them is called pyridinium chlorochromate. Okay, so because of this pyridinium group here, it dissolves in organic solvents, so it would dissolve well in something like methylene chloride or benzene. And this is known as PCC. Okay, so this is good at taking primary alcohols and making aldehydes. Now, if you're dealing with a secondary alcohol, it doesn't matter if you have water in there or not, because you can only oxidize it only to a ketone. You can't further oxidize it. So this will naturally, of course, take secondary alcohols and convert them to ketones. But it's still using that toxic material. It's a little bit, harsh too, even though we're using organic solvents. So are there some other methods to do so? Definitely there are. And we're going to talk about something called the Swern oxidation, which is a great method to oxidize using a collection of solvents, using things like dimethyl sulfoxide, oxalochloride. The lights just turned off for a second, not sure why. But anyways, let's not get distracted. Let's talk about Swern oxidation. Swern oxidation is a really nice reaction. You have an alcohol, you have this molecule here called DMSO, dimethyl sulfoxide, and then oxalochloride. And you typically add a base, like a tri-substituted base like triethylamine. So if you mix these things together, what you're going to end up generating is an aldehyde. And these are done under anhydrous conditions. Some other things that we do in this reaction is we take the DMSO and we pre-mix this with the oxalochloride first before we add the alcohol. Okay, and I'll explain why that is. Let's think of the mechanism of the Swern oxidation. All right, so the big hint is that we're going to mix these two together, and you might say, well, this looks like a great electrophile, right? You have this very reactive acyl chloride type functionality. Here you have DMSO, you might think, well, nothing really jumps out. Now let's draw DMSO in a slightly different orientation where we have resonance arrows going up to the oxygen. And we put a positive on the sulfur, negative on the oxygen. So we actually have a reasonable nucleophile that can now attack the oxalochloride. So what happens when that happens? So this O negative will come here, attacks one of these carbonyls. It doesn't matter which one because it's a symmetrical molecule. Form your tetrahedral intermediate. You have a Cl attached, and it's going to look just like this. Now, we're going to collapse that tetrahedral intermediate. Your best leaving group here is Cl. The chloride is going to leave. And the chloride is going to be left as an anion. So this is actually one of my favorite part of this next reaction. So you have this molecule here with very reactive functionality. You can see the electron density wants to move up this way. The sulfur is positive. It really would like to have electrons back. And so what happens is that we've now gone from this type of scaffold, which is a reasonable nucleophile, to this sulfur now being a pretty good electrophile. So what Cl- will do is it will attack the sulfur here. You can now break this sulfur-oxygen bond. Now, watch what's going to happen. We're going to form a double bond here between oxygen and this carbon. So now you can see here that this carbon will have 1, 2, 3, 4, 5 bonds. So we have to break a carbon bond. Okay, so we do that. We break this sigma bond here. And then we're going to break off this chlorine bond. So it's pretty cool because what you end up getting is this with a chlorine attached, positive charge on the sulfur. But your byproducts are, look at this molecule here. This molecule here is CO2, carbon dioxide. This molecule here that comes off is carbon monoxide, and then you generate Cl anion again. So what's really cool about this reaction is that when you initiate it, you know you're setting it up and it's going to be ready when you see the bubbles coming off in your reaction. And it's a highly efficient reaction because it's entropically favored, right? You're going from 2 molecules here and you're generating 1, 2, 3, 4 species. So it's entropically favored, highly favorable reaction. All right, so once we generate that species here, and you see those bubbles start to dissipate, this is when we can now add our alcohol. So here's our alcohol. And you can see here that we have our electrophile, which is the same type of electrophile that we had up there. The alcohol will come and react and do an SN2 reaction, displace off that chloride. And you have chloride in solution. Now you have a acidic proton here, and we need to remove it. Are we going to use Cl- to remove that proton? What do you think? If we try to do that, we're going to generate HCl, which is too strong an acid. Right? The pK of HCl is around -7. So in solution, we use our triethylamine, and triethylamine is our base that will come and remove that proton. And the pK of triethylamine is around 10. So that's a much weaker acid, and that's going to drive this reaction. pK of the conjugate acid is 10. The pK of this here, this proton being removed, is around -2. So you always follow which side the weaker acid-base pair falls on with respect to acid-base chemistry. Okay, when that happens, we're doing just simple deprotonation, and we're going to generate don't forget the positive charge is still on the sulfur, has 3 bonds here. Okay, and remember we need to go to an aldehyde. So we're almost there. How are we going to do that? So similar to the chromium species, take triethylamine. That's going to be our base, and this is going to come pick up the proton, form that double bond, and then what this is going to leave as is dimethyl sulfide. So that's pretty cool because that is also a gas. That's your product, your dimethyl sulfide. Looks like that. So it's also entropically favored. So that's the Swern oxidation. Really, really efficient reaction. Oxidizes primary alcohols to aldehydes. We'll take secondary hydroxyl groups and oxidize them to ketones. But what's nice is that you don't need harsh conditions like acid for that reaction to occur. Now the lights keep turning on and off a little bit freaky. It's so let me just play with it for a second. Anyways, at least these lights are working. So let's focus on that. All right, so a couple of things I want to mention with respect to the oxidation. You still use some molecules in the reaction. Even though you pre-mix these two together, this is really, really reactive. So if you have any functional groups on your molecule other than the alcohol that could react with this, you do run the chance that you might get some side products or side reactions occurring. So it is efficient, but are there some even more gentler ways to oxidize? And I wouldn't be saying that if there weren't, so there definitely are. So let's take a look at a different type of oxidation. This one is called Desaulniers Periodinane, Desaulniers or DMP oxidation. Often abbreviated as DMP. So you use this structure that I guess I'll just draw, and it uses this this pentavalent iodine. Let me redraw this. All right, so that's Desaulniers periodinane reagent. It's a great way to oxidize. How does it work? Okay, so we have this pentavalent iodine, and what's attached to most of the groups are these acetate groups, even up here through this cycle. In all these acetate groups, you know that there's resonance occurring this way in all of them, right? So electron density is being pulled through all of these, okay? So therefore, what this means is that this, this iodide has this partial positive character to it, meaning that it's a pretty good electrophile. And recall that iodine is at the bottom, or not the bottom, but it's low in that group 7. So it's actually, it's actually a pretty big atom. So what happens is that you have your nucleophile, and it's going to react at the iodine, and then you're going to kick off one of these acetate leaving groups. So let's take a look at what that's going to look like. So we basically just we've done a swap with the alcohol with one of the acetate groups. We have a positive oxygen because that proton still remains there. What's going to be the base that removes it? The base that removes it is you now have acetate in solution. So acetate, which is the conjugate base of acetic acid, can very easily just remove that proton. No problem. All right, so just going to draw that all the way down here after that proton transfer. Okay, how are we going to go from this complex to an aldehyde? All right, so just to be clear, we're going from this alcohol, this Martin periodinane, to an aldehyde. So we need to find that acidic proton that we can remove. Here are a couple acidic protons, right? So how are we going to remove that? So basically, what you can think of is that you have this double bond here, which could come pick up that proton, right? If it picks up that proton, form a double bond there. That's the beginning of how that aldehyde's formed, right? And then this will come down to the iodine, and then you'll break off this iodine-oxygen bond. Okay? So it's kind of like this concerted mechanism that happens through intramolecular deprotonation. Okay? So you can think of, again, removing that acidic proton, forming the double bond, breaking the oxygen-iodine bond, and then you have to break now this new iodine-oxygen bond. So you do that, and you generate your aldehyde, plus your spent molecule. Which will just have three things attached to it. Attached to the iodine. Okay, so that's not going to be useful anymore, but that doesn't matter because all you care about is your product here, which is the aldehyde. So DMP is actually pretty, it's a bit dangerous to make the compound. I don't have time to talk about how it's made, but you can purchase it. It's a little bit expensive, but it's pretty gentle and mild when you use it. And as you can see, you don't use any harsh conditions whatsoever, and it dissolves in organic solvents. So that's so that's one nice way to do that. And then the last one I just want to talk to you about is a metal catalyzed method to oxidize again primary alcohols to aldehyde. That's what we're working on exclusively here, so we don't get the full oxidation. Okay, so we can use something called, we call this, abbreviate this as TPAP. It stands for tetrapropyl ammonium peruthenate. So what is that? Peruthenate. Okay, so what the structure is you have this positively charged nitrogen, and then it's complex to this negatively charged ruthenium compound, which is in the +7 oxidation state. Okay, so these two complexes together, and it's It's a ruthenium type of metal, and how it's going to work is as follows. Again, you're going to take your alcohol, and it's going to essentially take this compound and go all the way to an aldehyde. And what you need to use with this is just a catalytic amount of the ruthenium. And I'll explain in a second why we use catalytic amounts and how we can regenerate it. Okay, so the first thing that happens is you're going to get, similar to that chromium type of reaction, you're going to get nucleophile to the electrophile. Okay, so you have your positively charged oxygen here, and then you're going to have some type of base that can come, remove that proton like we've seen many times already. I'll just put the negative charge here. You'll see why in a second. In order for us to form a double bond, we're going to do a very similar type of thing, a variation on a theme that we've seen already. So we'll always need to deprotonate and pick up the proton, form a double bond. The thing that's going to do that is a negative charge of the oxygen that's attached to the ruthenium. And that will generate your aldehyde plus this ruthenium species. And something that looks like this. All right, so that's your desired product. Bingo, you've made it. And this ruthenium complex here will actually, again, pick up another proton. You'll lose water, and you'll generate this compound here, which is actually ruthenium 5. And this is actually inactive. And you might say, well, doesn't matter, right? But I told you this is catalytic. And the reason we have to do this under catalytic conditions is because the ruthenium is just really, really precious, really, really expensive. It costs a lot of money for this ruthenium, for this metal. And if you're using stoichiometric amounts, you'll just break the bank. So we have to use very, very small amounts of it. But there's a problem, right? Because you can see for every molecule that gets oxidized to an aldehyde, we generate an inactive compound. So I'll write that down. This is inactive. This is active. So that's a bit of an issue. So what we need to do is we need to think of a way to go from this inactive complex and reactivate it so that we can get another ruthenium compound in the +7 oxidation state so we can continue that oxidation process. So this is where this compound called NMO comes into play. So NMO stands for N-methylmorpholine N-oxide. And this is actually used to regenerate the active form of the catalyst. So we add NMO to this reaction, So don't worry, I'll draw out the whole reaction of all the components that we need. But what's nice about this complex here is that this NMO is actually relatively cheap. So how do we regenerate that? Okay, so we have this negative oxygen, and it's going to react at this ruthenium core, like I'm showing you here. And what we're going to have is this type of reaction. Now, ruthenium has a number of electrons on its outer shell, and essentially what's happening is that electron density is being pulled away over here because of this NMO. So what it's going to do is it's going to form a double bond here, and then it's going to break this oxygen-nitrogen bond. And you generate this compound, which is useless, but we don't really care about that. But what's more important is that you regenerate this ruthenium compound in the +7 oxidation state. This is now active, and then this can go out and seek another alcohol and continue that process. So this reaction, to summarize, takes an alcohol, and you'll typically see TPAP with NMO, and it's implied that we're using catalytic TPAP because we don't have, hundreds or thousands of dollars for a single reaction. And it's very gentle and very mild, and we can generate our aldehyde like I'm showing you. So if we had a secondary alcohol, this would get oxidized to a secondary or to a ketone. I think that's everything I want to mention about TPAP. All right, so to summarize this unit here, we've taken alcohols. You can imagine also a secondary alcohol. And if you want to oxidize this all the way to a carboxylic acid, you've learned good ways to do so, right? You can use things like Jones oxidation, or you can use KMNO4, or we can use a dichromate with strong acid and water, so that would work pretty well. If you wanted to take this alcohol, but you want to stop at the aldehyde, then you can use things like pyridinium chlorochromate, PCC, or you can use things like, TPAP, NMO is good. You can use things like Desaulniers, Periodinane, or you can use things like Swern oxidation. Okay, and this also works really well for secondary alcohols because you will generate a ketone. And finally, if you take secondary alcohols and you undergo these same conditions like Jones or KMNO4, you will also generate the ketone. So it really depends what type of molecule you want to make, and depends how harsh you want those conditions to be, how harsh you want those conditions. These conditions on the left are anhydrous, there's no water present, whereas these ones are typically aqueous, and they're typically done with acid to help promote that reaction. Okay, so that's really what I wanted to talk to you about with respect to oxidations. So let's end this lecture here. I'll just have a short lecture 9 on just some other elements in terms of controlling chemoselectivity. Thanks for tuning in, and see you soon.